Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will learn how to apply integrated rate laws in a word problem type setting. To begin, we will quickly review the half-life and integrated rate law equation for each order of reaction. So let's go ahead and look at the equations for first order. So the first equation that you guys are seeing is the equation for the half-life for first order reactions, where T1 half is going to equal to the natural log of 2, divide this by the rate constant K. And so if you guys recall, T1 half is representing the amount of time it takes for the reactant to reach half of its original concentration. And so T1 half is always going to be in units of time, where it can be seconds, minutes, hours, and the list continues. And so natural log of 2 is something that you guys can just type in the calculator. And what you guys will get is essentially this number. I do want to let you know that there are a whole bunch of other digits past the 3. So sometimes for precision, you guys should just type in natural log of 2 and press enter and then divide that by the rate constant K if you guys are trying to determine the half-life or the amount of time it takes for the reactant to reach half of its original value. And so last but not least, K is going to represent the rate constant. And so the units for the rate constant under first order reactions is going to be the 1 over some time unit, whether it's going to be seconds, minutes, or hours. It just really depends. And so what I do want to note is that this form is equivalent to this form. So you guys can just choose one or the other. Either you type in natural log of 2 and then divide that by K if you're trying to solve for the half-life, or you guys can just put in 0.693, divide that by the rate constant K if you wanted to solve for the half-life. All right, so looking at the integrated rate law for first order, we have a few forms. And so each and every single one of these forms that you guys are seeing is equivalent. And so the only thing that's different is how they're arranged algebraically. And so sometimes using this form is easier. Sometimes using this form is easier. And I'll go ahead and talk about this form in just a second. But basically, this form just transitions this equation from this shortened form to the straight line plot. All right, so looking at this equation, when you guys are trying to work with this equation, this fraction right here is being natural logged. So the whole thing is being natural log. And so when you guys are putting this in your calculator, you might want to work within the parentheses first before you take the natural log of that value. All right, so looking at the denominator, this denominator is describing the initial concentration of that specific reactant. And so in terms of a percent, you guys can think of the initial concentration as 100%. So sometimes you guys can use this value if the question is asking you to express your answer in terms of percent. But if it's asking for a specific concentration, then you guys cannot use 100%. and you might have to actually calculate what that concentration is. And so in the numerator, we have A sub t, which is representing the concentration of that reactant at any time period. And we saw a little bit of that in the previous lecture video. So K is going to once again represent the rate constant. So notice how the rate constant K is found in the integrated rate law as well as the half-life equation. So you guys can use the rate constant K as kind of the ambassador between both of these equations. Last but not least, we have T, which is any unit of time. And so this time is not the same as the half-life. And so T1/2 is specific to the amount of time it takes for the original concentration to reach half of the original value. And so T, time, is just any period of time that's outside of the half-life. All right. And so if you wanted to expand this shortened form of this equation, you're going to go ahead and apply some rules of natural log. In other words, if you divide two terms that is being natural logged, these two terms, when expanded, are going to be subtracted. And so here we have the natural log of the concentration of A sub t minus the natural log of the initial concentration. And that's going to equal to negative kT. And so we can go ahead and isolate the natural log of the concentration of A at any time period by moving this term to the other side. And so for us to move that term, we're going to have to add natural log of A sub 0 to both sides of the equation. And when we do so, we essentially get this equation, where the natural log of A sub t is already solved for, and that's going to equal to negative kT plus the natural log of the initial concentration. And so this form is known as a straight line plot, or the expanded form for the integrated rate law, where you can overlap the equation of the line such that the y-axis is equal to the natural log of the concentration of A at any given time period, which is equal to the slope, which is going to be the rate constant K, times that by t, which is going to be on the x-axis if you're plotting it on a graph, plus b, which is the y-intercept. And so we saw how we can apply this equation in the previous lecture video. And so it doesn't really matter which form you guys choose for first order reactions. It just really depends on the question. So sometimes this form is much easier to work with in word problems. This form might be easier to work with when you're graphing the first order, when you guys are graphing first order reactions. But you can also use this form when you're working with word problems as well. The only difference is the types of operations you guys would perform when trying to isolate a specific variable. In other words, solving for this term or solving for k solving for T, solving for initial concentration. All right, so looking at the equations for second order, once again, we see half-life. And so we know that the half-life is going to be in units of time. Okay, so it's the same. And here we see the rate constant K, and it's being multiplied by the concentration of reactant A. And so I'll just go ahead and put in half-life, which is always in units of time. K is the rate constant. And then this is going to be the concentration of the reactant. And so that's pretty much it for the half-life equation for second order. There's nothing special about it. You do not take the natural log of 2 or anything like that. So just follow this equation and try to solve for the term that you guys are looking for. And so these two forms represents the integrated rate law for second order reactions, in which the top form is equivalent to this form of first order reactions. And this bottom form is going to be the straight line plot, or the expanded form, for this integrated rate law. And so very similar to first order, you guys can go ahead and use either this form or this form when you guys are working through word problems. The only thing that changes is the type of algebra that you guys are going to be performing. So sometimes it's much easier to work with this specific form of the equation. Sometimes it's easier to work with this form of the equation. It just really depends on the problem. And so all the terms are pretty much the same. So this is A sub T, any concentration at, the concentration of reactant A at any given time period. And then this is going to be the initial concentration. And this is the rate constant K. And this is T, which is time. And so this T is not the same as T1 half. Okay. All right, so looking at zero order, you have the half-life. And so once again, half-life is expressed in units of time. Concentration is expressed in units of molarity. And K is going to be the rate constant. And so looking at the integrated rate law for zero order, this is actually the expanded version of the integrated rate law, or this is the straight line plot version of the integrated rate law, where this is going to represent the y-axis. If you're trying to plot this, negative K is going to represent the slope. T is going to represent time, it is time, but specifically the x-axis on a graph. And the initial concentration is going to be the y-intercept. And so if you guys are trying to use the shortened version of the zero order reaction, it's simply going to be A sub T minus the initial concentration, which is equal to negative K times T. Okay, and so I'm going to zoom out real quick. So this shortened version of the integrated rate law for first order is analogous to this form for second order, which is analogous to this form for zero order. This form, and this form are all of the expanded forms for the integrated rate laws. And you guys can go ahead and use those equations that I just circled. I'll circle them again to test for the order of reaction. but you guys can also use that form for solving integrated rate laws in a word problem type setting. So I'll just go ahead and put a note that everything here is going to represent the y-axis, positive k is going to represent the slope, t is going to represent x, and this whole fraction right here is going to represent the y-intercept. All right, and so now that we've taken a more detailed look at the equations for first, second, and zero order reactions, let's go ahead and work through 4 problems that will allow us that will showcase how to use these equations to solve for a specific variable. All right, so let's go ahead and look at the first problem. Dinitrogen pentoxide decomposes to form oxygen gas and dinitrogen tetroxide. The reaction has the following rate law, in which the rate is equal to K times this by the concentration of dinitrogen pentoxide. So it looks like dinitrogen pentoxide is the reactant. At 55 degrees Celsius, the first half-life of this reaction is 95.61 seconds. And so if the initial concentration of dinitrogen pentoxide is 0.150 molar, how much time will it take for the concentration to drop to 0.0125 molar? And how much is this in minutes? All right, so the first thing that I'm going to do is I'm going to list the given values. And so it looks like they gave us the half-life. So the half-life of this reaction is 95.61 seconds. So I'm just going to put in T1 half is equal to 95.61 seconds. They also gave us the initial concentration. So I have N2O5. So that's the initial concentration, which is equal to 0.150 molar. And so notice how it's asking for time. Okay, so I'm looking for T, not T1 half. How much time will it take for the concentration to drop to this amount? And so since this is the final concentration, I'm going to assume that N2O5 sub T, the concentration at any given time period, is going to be 0.0125 molar. Okay. All right. And so looking at this question, did it tell us explicitly what order of reaction we're going to be using? Okay, so there are a whole bunch of equations that we can use to determine time. But for us to determine which equation that we're going to be using, we first need to determine what order of reaction this specific chemical reaction is undergoing or following. And so looking at this question just a little bit in greater detail, notice that the rate law was given to us. And remember that the rate law describes the order of reaction. And so looking at dinitrogen pentoxide, notice how there's no number in the exponent. And so whenever you guys see that, it means that there's an invisible 1. And so this rate law is telling us that this reaction is undergoing first order kinetics. And that is a critical information that we need because it now allows us to focus on which equation we're going to be employing And so since the equation is undergoing first order kinetics, I'm going to be using this, and I'm going to be using this, right? Or you guys can use this and this, doesn't really matter. But for now, I'm just going to go ahead and use the shortened form of the integrated rate law. So once you guys have determined the order of reaction, all of the equations that's related to first order should be written down. So T1/2 is equal to natural log of 2 over the rate constant K. And the natural log of the concentration of dinitrogen pentoxide at any given time period, divide that by N2O5, the concentration of dinitrogen pentoxide at the initial time period, is equal to negative times this, negative K times that by T. Okay. All right. So now that we've figured out the equation that we're going to be using and we've listed all of the known values, what we're going to do is we're going to start plugging things in. And so notice how I have a value for T1/2, and I have a value for the initial concentration, and I have a value for this concentration, and that's found in the numerator. And so the question is asking us for us to determine T, which is this. And so there's one piece of information that this question has not yet given us, which is the rate constant K. And so since we know the half-life, we can solve for K, and then once we solve for K, we can go ahead and plug it into the second equation. And since we have a value for this term, and this term, we can just go ahead and solve for T. So that's basically the game plan. So I'm going to go ahead and replace T1/2 with 95.61 seconds. And that's going to equal to the natural log of 2 over the rate constant K. And so I'm going to go ahead and solve for the rate constant K by multiplying K to the other side and then dividing by 95.61. And so the rate constant K is equal to the natural log of 2 over 95.61 seconds. And so if I plug that into my calculator, I'm going to get 7.250 times 10 to the negative 3, 1 per second. Okay? And so the reason why it's 1 per second is because second is in the denominator. And so now that I've figured out the rate constant K, I can go ahead and plug that into my integrated rate law, where the natural log of the concentration of dinitrogen pentoxide at the final time period is going to be 0.0125 molar, while the initial concentration is going to be 0.150 molar. So notice how the molarity unit cancels out. And that's going to equal to negative K, which is what we just figured out, 7.250 times 10 to the negative 3 times this by T. And so we can go ahead and divide what's inside this parentheses, and that's going to give us the natural log of 8.33 times 10 to the negative 2. So notice how I'm trying to record the correct number of sig figs. And then that's going to equal to negative 7.250 times 10 to the negative 3 times this by T. And so if I were to plug this into my calculator, I'm going to get negative 2.485. And so if you guys recall the rules for natural logs for sig figs, if there are 3 significant digits, then that means you need to record 3 places after the decimal. So this whole number 2 does not count as a significant digit. And so that's going to equal this term. And then I'm just going to go ahead and solve for t by dividing both sides by this value. And so if I plug that in, I get a time value. Actually, you know what? There's one thing that I'm missing here. I'm missing the unit. So 1 per second, 1 per second, 1 per second. And so if I were to divide negative 7.25 times 10 to negative 3 to the other side, this second would be flipped to the very top. So the final answer is going to be 342.7 seconds. And so this is how much time it's going to take for the original concentration, 0.150, to reach 0.0125 molar. Okay? So that's pretty powerful because now we can kind of quantify how much time it'll take to go from one concentration to another concentration. And so the second part to this question is asking us to express our final answer in minutes. And so this is a quick dimensional analysis where we have 342.7 seconds. Now, for every, so we're going to go from seconds to minutes. And so for every 60 seconds, that's going to give us 1 minute. And so if I divide 342.7 by 60, I get 5.712 minutes. All right, and so in terms of sig figs, this 60 seconds, that's considered an exact number. And so we're going to go ahead and ignore the number of significant figures. And so we should report 4 sig figs at the very end of the calculation. All right, so hopefully this gives you guys an idea of how to incorporate these integrated rate laws and these half-life equations for these word problems. All right, so let's go ahead and take a look at another example. And so here we're still working with dinitrogen pentoxide. And the rate law is given to us. And so therefore, we know that it's still undergoing first order kinetics. And so once we know the rate law is undergoing first order kinetics, we can go ahead and write down all the equations that's related to first order. And so I'm going to cheat a little bit over here, and I'm just going to just copy this so I don't have to rewrite it again. Okay. So now that the equations for first order is written down, I'm going to go ahead and list out all the given values. And so at 45 degrees Celsius, the rate constant is this value. So in this particular problem, the rate constant K is already given to us. So K is going to be 6.22 times 10 to the negative 4, 1 per second. And so we can also take a look at the units for K. And so if it's 1 per second or 1 per minute or 1 per hour, basically if it's reciprocal of time, that's also another characteristic of first order reactions. And so if the initial concentration of this compound is 0.500, what will the concentration be after 1 hour? And so here in this case, what we're solving for is dinitrogen pentoxide after 1 hour has passed. Okay. And so let's go ahead and plug in these values here. And so here we have the natural log of, let me just zoom in, the concentration of N2O5 after 1 hour has passed, over the initial concentration. And so they told us that the initial concentration is this value. And so that's going to be 0.500 molar. And that's going to equal to negative K. So that's going to be the 6.22 times 10 to the negative 4. And the unit is 1 per second. And the T, or time in this case, is going to be 1 hour. And so I've kind of expanded 1 hour to 1.000 for sig figs. And so I'm just going to go ahead and multiply this by 1.000 hour. Now, if you guys notice, the units for time is not the same. And so it's really important for you guys to just write your units just kind of as a measure, or as a check to see if those values are supposed to be the values that you're going to be writing down. And so since the units of time is different, I'm going to go ahead and convert hours into seconds. And so for every 1.000 hour, that's going to give me, let's see here, so for every 1 hour, that's equal to 60 minutes. For every 1 minute, that's going to give me 60 seconds. So notice that all of the units cancels except for seconds. And so overall, that's going to give me 3,600 seconds. So I'm going to go ahead and copy this whole thing. And I'm going to replace the hour with 3,600 seconds. And so now seconds will cancel. And so if you plug this into the calculator, this is going to give you negative 2.2392. And so since there are 3 sig figs here, I'm just going to round this up to negative 2.24. And then that's going to equal to the natural log of the concentration of N2O5 at 1 hour over 0.500 molar. All right, so to solve for this variable, we're going to have to first break it out. And so the opposite of natural log is e, so you're going to e both sides. And so you guys are going to plug this into the calculator. And so what you guys are going to be left with is simply 0.11. Now for sig figs, if you guys are taking the anti-natural log, if there are 2 places after the decimal, then that means you need 2 sig figs. So 2 decimal places, and that's going to equal to 2 sig figs. And so that's going to leave us with the concentration of N2O5 over 0.500 molar. And so you guys are going to simply solve for this term, and you're going to multiply 0.5 over to the other side. And so the final answer that you guys are going to get, so this is the concentration of N2O5 after 1 hour has passed, is equal to 0.053 molar. Okay. All right, so notice the unit molarity is now going to be in the numerator, giving us our final unit for this value. And so what we want to do is we want to make sure that our answer makes sense. And so after 1 hour has passed, remember that 0.500 molar is the initial concentration. And so after 1 hour has passed, it would make sense that the final concentration is much smaller than the initial concentration. Okay, if it's greater than 0.500, then that doesn't make sense logically. So reactants are going to be consumed. All right, so let's go ahead and take a look at another problem. So in this case, we have the decomposition of hydrogen peroxide, which has a rate constant of this specific value. So we're going to determine the percent of hydrogen peroxide that has decomposed in the first 550 seconds. All right, and so remember these are integrated rate laws, and there are several different types. There's first order, second order, zero order. And so does this problem explicitly say which order of reaction we're going to be using? The answer is no, it's not explicit. However, if you guys look at the rate constant K, remember the unit for the rate constant K can also describe or inform the reader what order of reaction is taking place. And so notice that the value of K is going to be 8.930 times 10 to the negative 4 per second. In other words, 1 per second. And so if you have 1 per second as your unit, this is already indicating that the reaction is undergoing first order. And so if it's molarity per second, then that's zero order. If it is 1 per molarity times second, that's describing second order. Okay. So please make sure you guys are familiar with these subtle characteristics of first, second, and zero order, because I can definitely give you one of those things, and you're just going to have to kind of sift through the problem to determine which order of reaction is taking place. And so if you're very familiar with all of the characteristics that describes first order, second order, and zero order, you guys will have an easier time in terms of working through these integrated rate law problems in a word problem type setting. All right, and so this question is asking us to determine the percentage of hydrogen peroxide that has decomposed in the first 550 seconds. So now that we know that this is a first order reaction, we're going to go ahead and write all of the equations that corresponds to first order kinetics. So we know that the half-life for first order kinetics is going to be natural log of 2 over the rate constant K, and that the natural log of the concentration of hydrogen peroxide, which is H2O2, at any given time period is going to be divided by the concentration of hydrogen peroxide at the initial time, so initial concentration. That's equal to negative K times S by T. And so since we're trying to determine the percent of hydrogen peroxide, what we're really solving for is the ratio between the numerator and the denominator. So this whole term is what we're solving for. And so all we really need is K and T. And so K is already given to us, which is going to be 8.930 times 10 to the negative 4, 1 per second, times this by time. And so it looks like they already gave us the time, which is in seconds. So this is 550.0 seconds. And so if you multiply both of these two, the second unit will cancel out, so the term becomes unitless. And what we get is simply negative 0.4912. And so this answer is unitless. And so that's going to give us the natural log of this whole thing. Okay. And so to solve for the ratio, we're going to e both sides. And so since there are 4 decimal places, we're going to record 4 sig figs. So I'm just going to go ahead and copy this right here. And so if you plug this into your calculator, you're going to press natural log or second natural log to bring up the e function. And then you're going to type in negative 0.4912. And then that's going to give us 0.6119. And so when you're solving for the ratio of hydrogen peroxide, this is representing the percent, or sorry, let me take a step back here. So the question is asking the percent of hydrogen peroxide. And so the answer that we have right now is not a percent, it's expressed as a decimal. And so to express this as a percent, we're going to go ahead and multiply by 100. So really the answer is going to be 61.19%. And so this answer is actually not the final answer. It's just going to get us there one step closer. And so whenever you guys are trying to solve for the ratio of your reactant between some period of time and the initial concentration, what this is really describing is the percent that remains. Okay, so you always have to keep that in mind. And so basically this is telling you that after 550 seconds has passed, this is the percent that remains. Okay? And it's always describing the percentage that remains. But the question is asking us how much has decomposed. And so basically, you're going to take this value and subtract it from 100. Okay? And so if you subtract it from 100, you get 38.81% that decomposed in the first 550 seconds of this reaction. And so this is your final answer. Okay? And so basically, I'm trying to showcase through these different types of problems, different types of questions that can be asked for integrated rate laws. I can't cover all of them, but these are just the highlights, if you will. All right, so we're going to go ahead and look at one last problem here. And so here the reaction. So here we have reactant A being converted to B and C. And in this problem, it's actually telling us explicitly that this is undergoing first order kinetics. And so after 50 minutes, and once again, I'm kind of expanding out 50 as 50.0 just for sig figs, the reaction is 25% complete. So if the initial concentration is 0.250, the question is asking us to calculate the rate constant K for this reaction with the correct units. And so since we're undergoing first order kinetics, we're going to go ahead and write all of the equations down that's relevant for first order kinetics. And so sometimes you guys actually won't need to use the half-life equation. I don't think we needed to use the half-life equation for this problem and for the previous problem. But you just always want to write down the half-life equation just in case you need it. And so for this problem, it looks like we were able to solve for the final answer just by using the shortened version of the integrated rate law. And the same can be said for this. And so you guys will know when to use the half-life equation if the question asks you to solve for the half-life, or the rate constant is the only other variable that's missing besides the variable that you're supposed to solve for. Okay. And so just for consistency, I'm going to go ahead and write the half-life equation for first order. So that's T1/2 is equal to natural log of 2 over the rate constant k. And so I'm going to go ahead and write the equation for the integrated rate law with respect to A, since this is my reactant. All right, so it looks like some values are given to us. So time t. So notice how after 50 minutes is not, this 50 minutes is not the half-life. It's just describing the time. If 50 minutes was the half-life, it would tell us in the problem explicitly. And so t is going to be 50.0 minutes. And what we're going to do is we're going to calculate the rate constant k. So we're going to go ahead and keep that as a variable. And so it looks like we have an initial concentration of 0.250. So the natural log of this guy divided by 0.250 molar. Okay. And so after plugging in all the information that's given to us explicitly from the problem, this is what we get. This is what remains. And so here, for us to solve, so this is what we're really solving for. And so for us to solve for, or I'm sorry, no, I take that back. Okay. So we're going to calculate the rate constant k. So this is what we're truly solving for. And so for us to solve for the rate constant k, we need to figure out this concentration term. And so the last piece of information that I haven't incorporated yet is this value right here, 25% complete. So if you guys are looking at the course of this reaction, so remember the concentration of A is on the y-axis and time is always on the x-axis. For first order kinetics, there's going to be an exponential decay. And so it's telling us that this reaction is 25% complete. And so I'm just going to arbitrarily put this 25% somewhere in here. So this is 25% complete. And so if this reaction is 25% complete, then that means that there is 75% that remains. And remember, this term right here is always referring to how much remains. And so if I wanted to figure out this A sub t, this portion right here, I can go ahead and take the initial concentration, which happens to be 0.250 molar, and multiply it by how much remains. And so 0.250 molar is the initial concentration. And if I multiply it by 0.75, that's going to give me 0.1875. So 2 sig figs is my least. I'm sorry. Let's just do 3 sig figs. So this is 25. Oh, is my screen frozen? I think so. All right. Let me see here. Okay. All right. So basically, where was I? So if I take this to be 25.0%, then if you subtract that by 100, that's going to be 75.0%. So I'll just work with 3 sig figs. Okay. So this is going to be rounded up to essentially 0.188. And so this is the concentration that remains, which is going to represent the concentration of A sub T. And so what I have really is natural log of 0.188 over 0.250, and that's equal to negative k times this by 50 minutes. And so I can go ahead and divide these two. And so if I were to divide 0.188 by 0.250, that's going to give me negative, I'm sorry. So let me go ahead and plug this in my calculator. So 0.188, divide this by 0.250. And then I'm going to take the natural log. So that's going to give me natural log of 0.752. And so here, that's going to equal to negative k times this by 50 minutes. And so if I take the natural log of my answer, then I'm going to go ahead and get negative 0.285. Okay, so that's equal to negative k times this by 50 minutes. Okay. And so here in this case, since I have 3 places after the decimal, since I have 3 sig figs, I need 3 places after the decimal. Okay, so 3 decimal places dp. And so what I'm going to do is I'm just going to solve for k. And so k is going to equal to negative 0.285. Divide this by negative 50.0. And so I apologize, I didn't put in that 0. So there's that lingering 0 that I did not put down. I'm doing that for sig figs, and so therefore the value for k is going to be, let's see here, divide this by 0.50. Okay. So it's going to be 5.70 times 10 to the negative 3. And in regards to the unit, notice that the unit minutes is with 50, so it's going to be down at the bottom. And so since there's nothing at the top, the unit will simply be 1 per minute. All right. Cool. So hopefully you guys were able to follow my train of thought and my logic. Apologize for the technical glitch. And so all 4 of these examples, highlight different scenarios that you guys can encounter on an exam. There's so many other scenarios out there. And if you guys have noticed, all 4 of these examples only dealt with first order kinetics. And so remember that there are second order and zero order kinetics that you have to also take into consideration. And so please work on those worksheets. Make sure that you guys are able to discern and know how to use these second order integrated rate laws, as well as the half-life, as well as the zero order integrated rate laws, as well as its half-life. All right, so that's it for now for this lecture video. We're going to go ahead and take a look at collision theory in the next lecture video. Bye.